Grid computing. Unit 2. Web services and grid monitoring are two important components of grid computing. Web services. Web services are used to provide interoperability between different software applications and services. They enable communication between different software applications, regardless of the programming languages or platforms they use. Web services are a key component of grid computing, as they allow different resources in a grid environment to communicate with each other. Grid monitoring. Grid monitoring is the process of monitoring the performance of grid resources to ensure that they are operating efficiently and effectively. Grid monitoring involves monitoring the performance of different resources in a grid environment, such as computing nodes, storage devices, and network bandwidth. This helps to identify any potential issues or bottlenecks in the grid and allows for proactive management to ensure the best possible performance. Web services and grid monitoring are closely related in grid computing, as web services are often used to facilitate communication between different monitoring components in a grid environment. Grid monitoring systems use web services to collect and exchange information about the performance of different resources in the grid, and to coordinate the monitoring and management of these resources. The use of web services and grid monitoring helps to ensure that a grid environment is functioning optimally and allows for efficient resource utilization and management. The Open Grid Services Architecture, OGSA, is a framework for building distributed computing systems that can work together seamlessly. It provides a set of standards and guidelines for designing, deploying, and managing grid computing environments. OGSA is designed to be an extension of the web services architecture, building on the existing standards for web services such as Simple Object Access Protocol, SOAP, Web Services Description Language, WSDL, and Universal Description, Discovery, and Integration, OD. The key components of OGSA include service-oriented architecture. OGSA is based on a service-oriented architecture, SOA, which means that software components are exposed as services that can be invoked by other software components. These services can be combined to create larger applications. Grid services. OGSA defines a set of interfaces for building grid services, which are services that can be accessed from anywhere on the grid. Resource management. OGSA includes a set of interfaces for managing resources on the grid, such as computing resources, storage resources, and network resources. Security. OGSA provides a framework for ensuring security on the grid, including authentication, authorization, and encryption. Workflow management. OGSA provides a set of interfaces for managing workflows on the grid, including the ability to define, schedule, and monitor workflows. OGSA provides a standardized way for building distributed computing systems that can span multiple organizations and locations. It allows organizations to share resources and work together in a seamless and efficient way. OGSA services are software components that are designed to be accessible over a grid computing environment. OGSA defines a set of standard interfaces that these services must implement in order to be interoperable with other services on the grid. Here are some examples of OGSA services. Grid Service Factory. This service is responsible for creating and managing grid services. It provides an interface for creating new services, monitoring their status, and managing their life cycle. Grid Resource Management. This service is responsible for managing grid resources, such as computing resources, storage resources, and network resources. It provides an interface for discovering available resources, allocating resources for specific tasks, and monitoring resource usage. Grid Workflow Management. This service is responsible for managing workflows on the grid. It provides an interface for defining workflows, scheduling workflow executions, and monitoring the status of workflows. Grid Data Management. This service is responsible for managing data on the grid. It provides an interface for storing, retrieving, and managing data in a distributed and scalable way. Grid Security. This service is responsible for ensuring security on the grid. It provides an interface for managing user authentication and authorization, encrypting data transfers, and managing security policies. Grid Information Service. This service provides a directory of available grid services and resources. It allows users to discover available services and resources on the grid, and it provides information about the status and location of these resources. The Open Grid Services Architecture, OGSA, Schema is a set of specifications and guidelines for creating and deploying grid services that comply with the OGSA standards. The schema defines a set of interfaces, or APIs, that grid services must implement in order to be interoperable with other grid services and to work seamlessly within a grid computing environment. The OGSA schema is based on the Web Services Description Language, WSDL, and defines a set of extensions to the WSDL that are specific to grid services. These extensions include Service Data Types. OGSA defines a set of data types that are used by grid services to exchange information. These data types include standard types such as integers, strings, and booleans, as well as more complex types such as XML documents and grid service references. Grid Service Description. OGSA extends the WSDL with additional elements that describe the grid-specific features of a service, such as its grid identity, grid context, and grid service reference. These elements are used by other grid services to discover and access the service. Service Lifetime. OGSA defines a set of interfaces that grid services must implement in order to manage their life cycle, including creation, deletion, and notification of state changes. Security. OGSA includes extensions to the WSDL that allow grid services to define their security requirements and capabilities. This includes the ability to specify the authentication and authorization requirements for accessing the service. Resource Management. OGSA includes a set of interfaces for managing grid resources, such as computing resources, storage resources, and network resources. These interfaces allow grid services to discover and allocate resources as needed. The OGSA schema is an important component of the OGSA framework because it allows grid services to work together seamlessly within a distributed computing environment. By conforming to the OGSA schema, grid services can be discovered, accessed, and used by other services on the grid, regardless of their location or the specific technology used to implement them. The Web Services Resource Framework, WSRF, is a set of specifications and guidelines for building web services that manage stateful resources. It provides a framework for creating and accessing stateful resources over the web, and it allows web services to interact with these resources in a consistent and standardized way. The WSRF framework is based on a set of specifications, including Web Services Resource Properties, WSRP. WSRP defines a standard way to define and manage the properties of a web service resource. It allows clients to query and update the properties of a resource using standard web services interfaces. Web Services Base Faults, WSBF. WSBF provides a standard set of error messages that can be used by web services to report errors and faults. It defines a standard set of fault codes and messages that can be used to indicate the type and severity of the error. Web Services Resource Lifetime, WSRL. WSRL defines a standard set of interfaces for managing the life cycle of a stateful resource. It provides a way for clients to create, destroy, and update resources, as well as to query the state of a resource. Web Services Resource Transfer, WSRT. WSRT provides a standard way to transfer the state of a resource from one location to another. It allows clients to move a resource from one web service to another without losing its state. Web Services Notification, WSN. WSN provides a standard way for web services to publish and subscribe to events and notifications. It allows clients to register to receive notifications when certain events occur, such as the creation or deletion of a resource. The WSRF framework is used to build web services that manage stateful resources, such as databases, file systems, or other types of data stores. By providing a standard way to manage the life cycle of these resources and to transfer their state, the WSRF framework allows clients to access these resources in a consistent and standardized way. This makes it easier to build and deploy web services that manage stateful resources, and it enables clients to access these resources more easily and reliably over the web. The Web Services Resource Framework, WSRF, defines a set of web services interfaces and operations for managing stateful resources. The services provided by WSRF can be used to create, update, delete, and query resources, as well as to transfer their state between different web services. Here are some of the key services provided by WSRF. Create. The create operation is used to create a new stateful resource. It is typically used to create a new instance of a database, file system, or other type of data store. Delete. The delete operation is used to delete an existing stateful resource. It is typically used to remove an instance of a database, file system, or other type of data store that is no longer needed. Get resource property. The get resource property operation is used to retrieve the value of a specified resource property. It is typically used to retrieve metadata about the resource, such as its name, description, or type. Set resource property. The set resource property operation is used to set the value of a specified resource property. It is typically used to update the metadata of the resource, such as its name, description, or type. Query. The query operation is used to retrieve a set of resources that match a specified set of criteria. It is typically used to retrieve a subset of resources from a larger collection, such as a set of files from a file system. Transfer. The transfer operation is used to transfer the state of a resource from one web service to another. It is typically used to move a resource from one location to another without losing its state. Subscribe. The subscribe operation is used to register a client to receive notifications when certain events occur, such as the creation or deletion of a resource. These services are typically exposed through standard web services interfaces, such as Simple Object Access Protocol, SOAP, Web Services Description Language, WSDL, and Universal Description, Discovery, and Integration, OD. By using these services to manage stateful resources, developers can build more flexible and scalable web services that can be used to manage a wide range of data stores and other types of resources. The Web Services Resource Framework, WSRF, defines a set of XML schema definitions for creating and managing stateful resources. These schema definitions are used to describe the structure of the messages that are sent between web services and clients when managing resources. Here are some of the key schema definitions provided by WSRF. Resource properties. The resource property schema defines the structure of the XML elements used to represent the properties of a stateful resource. It includes definitions for the data types of each property, such as integers, strings, and dates. Resource property metadata. The resource property metadata schema defines the structure of the XML elements used to describe the metadata of a resource property. This includes information such as the name, description, and data type of the property. Resource property document. The resource property document schema defines the structure of the XML documents that are used to transfer the state of a resource property between web services. It includes the resource property metadata and the value of the property. Resource lifetime. The resource lifetime schema defines the structure of the XML elements used to manage the life cycle of a stateful resource. This includes operations such as create, destroy, and renew. Resource key. The resource key schema defines the structure of the XML elements used to identify a specific instance of a stateful resource. This includes information such as the name, type, and identifier of the resource. These schema definitions are typically used in conjunction with other web services standards, such as SOAP, WSDL, and OD, to create and manage stateful resources. By providing a standardized way to describe the structure of the messages used to manage resources, WSRF enables developers to build more flexible and scalable web services that can be used to manage a wide range of data stores and other types of resources. OGSA, Open Grid Services Architecture, and WSRF, Web Services Resource Framework, are two related but distinct technologies that are often used in the context of grid computing. Here are some of the key differences between OGSA and WSRF. Architecture. OGSA is an architecture for building grid systems, while WSRF is a framework for building web services that can be used in grid systems. OGSA provides a comprehensive architecture for building grid systems that includes many components beyond just web services, such as data services, information services, and computational services. Resource modeling. WSRF provides a standard way to model and manage stateful resources in a distributed computing environment, while OGSA does not have a specific focus on resource modeling. OGSA provides a broader framework for building grid systems, including mechanisms for resource discovery and monitoring, but does not define a specific approach to resource modeling. Protocol support. WSRF is based on existing web services standards such as SOAP, WSDL, and XML, while OGSA does not mandate the use of any specific protocols. OGSA is more flexible in terms of the underlying protocols that can be used to implement its various components. Compatibility. WSRF is compatible with OGSA, but OGSA is not dependent on WSRF. OGSA provides a more comprehensive architecture that includes many components beyond just web services, but WSRF can be used within an OGSA-based grid system to provide a standard way of modeling and managing stateful resources. In summary, OGSA and WSRF are two related but distinct technologies that can be used together in the context of grid computing. OGSA provides a comprehensive architecture for building grid systems, while WSRF provides a framework for building web services that can be used in grid systems, with a specific focus on modeling and managing stateful resources. Grid monitoring systems architecture refers to the overall design and components that make up a system used to monitor the performance of a grid computing environment. The architecture of a grid monitoring system typically includes the following components. Data sources. These are the sources of data that provide information about the performance and behavior of the grid computing environment. Examples of data sources include resource managers, schedulers, and applications running on the grid. Data collection. This component is responsible for collecting data from the various data sources. It may use monitoring agents installed on the resources or pull data from the data sources through APIs. Data storage. This component is responsible for storing the collected data. It may use a database, file system, or other data storage technology. Data analysis. This component is responsible for analyzing the data to identify patterns, trends, and anomalies. It may use statistical models, machine learning algorithms, or other techniques to process the data. Data visualization. This component is responsible for presenting the data in a way that is easy to understand and interpret. It may use dashboards, charts, or other visualizations to help users understand the performance of the grid computing environment. Notification and alerting. This component is responsible for notifying users when there are issues with the performance of the grid computing environment. It may send alerts through email, SMS, or other channels to inform users of issues and enable them to take action. Grid monitoring systems architecture typically involves the use of standard protocols and interfaces such as Simple Network Management Protocol, SNMP, Extensible Messaging and Presence Protocol, XMPP, and Simple Object Access Protocol, SOAP, to ensure interoperability with different components of the system. The architecture may also include features such as security and access control to ensure the privacy and security of the data being monitored. I have. Gridis is an open-source grid monitoring system that is designed to monitor and manage grid computing environments. It was developed by the Grid Computing Center at the Institute of Physics in the Czech Republic and is available under the Apache license. GGSIPU provides a range of features and functionalities for monitoring and managing grid computing environments, including data collection. GGSIPU collects data from various sources, such as resource managers, grid middleware, and job schedulers. Data analysis. GGSIPU provides data analysis tools that allow users to analyze data and generate reports on the performance of the grid environment. Data visualization. GGSIPU provides a web-based user interface that includes dashboards and visualizations to help users understand the performance of the grid environment. Job monitoring. GGSIPU includes job monitoring features that enable users to monitor the progress of their jobs and receive alerts when there are issues. Alarm and notification. GGSIPU provides alarm and notification features that allow users to configure alerts based on certain thresholds or conditions. Authentication and authorization. GGSIPU provides authentication and authorization features to ensure that users only have access to data and features that they are authorized to access. GGSIPU is built on a modular architecture, which means that users can add new plugins and modules to extend its functionality. The system is also designed to be scalable and can be deployed on small clusters or large-scale grid computing environments. VAMM, Job Analysis, Monitoring, and Management, is a job monitoring and management system for distributed computing environments, including grids, clusters, and clouds. It is an open-source project and is available under the Apache license. JAM provides a range of features and functionalities for monitoring and managing distributed computing environments, including data collection. JAM collects data from various sources, such as resource managers, job schedulers, and other monitoring systems. Data analysis. JAM provides data analysis tools that allow users to analyze data and generate reports on the performance of the distributed computing environment. Data visualization. JAM provides a web-based user interface that includes dashboards and visualizations to help users understand the performance of the distributed computing environment. Job monitoring. JAM includes job monitoring features that enable users to monitor the progress of their jobs and receive alerts when there are issues. Job management. JAM provides job management features that allow users to submit, cancel, and modify jobs. Resource allocation. JAM includes resource allocation features that enable users to allocate resources based on job requirements. Authentication and authorization. JAM provides authentication and authorization features to ensure that users only have access to data and features that they are authorized to access. JAM is built on a modular architecture, which means that users can add new plugins and modules to extend its functionality. The system is also designed to be scalable and can be deployed on small clusters or large-scale distributed computing environments. VMDS, Monitoring and Discovery Service, is a grid monitoring system that provides a framework for monitoring and discovering resources in grid computing environments. MDS is based on the Lightweight Directory Access Protocol, LDAP, and provides a standard way to publish and discover information about resources in a grid environment. MDS provides a range of features and functionalities for monitoring and managing grid computing environments, including resource monitoring. MDS provides a standardized way to monitor resources in a grid environment, including information about the resource's status, availability, and performance. Resource discovery. MDS provides a standardized way to discover resources in a grid environment, including information about the resource's location, availability, and attributes. Data collection. MDS collects data from various sources, such as resource managers, middleware, and job schedulers. Data analysis. MDS provides data analysis tools that allow users to analyze data and generate reports on the performance of the grid environment. Data visualization. MDS provides a web-based user interface that includes dashboards and visualizations to help users understand the performance of the grid environment. Alarm and notification. MDS provides alarm and notification features that allow users to configure alerts based on certain thresholds or conditions. Authentication and authorization. MDS provides authentication and authorization features to ensure that users only have access to data and features that they are authorized to access. MDS is designed to be scalable and can be deployed on small clusters or large-scale grid computing environments. It is also extensible, which means that users can add new plugins and modules to extend its functionality. Gridis, JAM, and MDS, Monitoring and Discovery Service, are all grid monitoring systems, but there are some key differences between them. Architecture. GGSIPU is based on a hierarchical, client-server architecture that includes multiple layers of data aggregation and processing. JAM is also a hierarchical system, but it is designed to be more modular and scalable than GGSIPU. MDS, on the other hand, is a distributed system that includes multiple data collection and processing nodes that work together to provide a unified view of the grid environment. Monitoring metrics. GGSIPU and JAM both provide a comprehensive set of monitoring metrics that enable users to monitor the performance of their grid environment, including system performance, network traffic, and resource usage. MDS also provides a range of monitoring metrics, but it is designed to be more flexible and extensible, and can be easily customized to support additional metrics. Visualization. GGSIPU includes a web-based interface that provides a range of visualizations and dashboards to help users monitor the performance of their grid environment. JAM also includes a web-based interface, but it is more focused on providing real-time alerts and notifications to users. MDS provides a range of visualization tools, but it is designed to be more extensible and customizable, and can be easily integrated with other visualization tools and applications. Resource discovery. GGSIPU and JAM both include mechanisms for discovering new resources in a grid environment and automatically adding them to the monitoring system. MDS also includes a resource discovery component, but it is designed to be more flexible and extensible, and can be easily customized to support additional resource discovery mechanisms. Integration with other tools, grid ICE and JAM are designed to integrate easily with other grid tools and applications, including job schedulers, resource managers, and other monitoring systems. MDS is also designed to be easily integrated with other tools and applications, but it is more focused on providing a flexible and customizable framework for monitoring and discovery services. Overall, grid ICE, JAM, and MDS are all powerful grid monitoring systems that can be used to monitor the performance of a distributed computing environment. Grid ICE and JAM are more focused on providing a comprehensive set of monitoring metrics and visualizations, while MDS is designed to be more flexible and extensible, and can be easily customized to support additional monitoring and discovery services. The choice between these systems will depend on the specific needs and requirements of the grid environment being monitored. Ganglia and Gridmo are both grid monitoring systems that are commonly used in distributed computing environments. Here are some of the key differences between Ganglia and Gridmo. Architecture. Ganglia is a lightweight, hierarchical monitoring system that is designed to be scalable and easy to deploy. It is based on a peer-to-peer architecture that enables data to be collected from many different sources and aggregated at a central location. In contrast, Gridmo is a more complex monitoring system that is based on a distributed architecture that includes a centralized data repository and multiple data collection and processing nodes. Scalability. Ganglia is highly scalable and can be used to monitor large-scale distributed computing environments with thousands of nodes. It is designed to minimize network traffic and processing overhead, and can be easily extended to support new data sources and monitoring metrics. Gridmo is also scalable, but its architecture is more complex and may require more resources to deploy and manage. Visualization. Ganglia provides a web-based interface that includes a range of visualizations and dashboards that enable users to monitor the performance of their computing environment. It includes a range of tools for monitoring system performance, network traffic, and other key metrics. Gridmo also provides a web-based interface, but its visualizations are typically less comprehensive than those provided by Ganglia. Resource discovery. Ganglia provides a mechanism for discovering new resources in a computing environment and automatically adding them to the monitoring system. Gridmo also includes a resource discovery component, but it may require more manual configuration and setup. Integration with other tools. Ganglia is designed to integrate easily with other tools and applications, including data analysis and reporting tools, as well as job schedulers and resource managers. Gridmo also supports integration with other tools, but its architecture may require more customization and configuration to achieve the desired level of integration. Overall, Ganglia and Gridmo are both powerful monitoring systems that are commonly used in grid and distributed computing environments. Ganglia is a lightweight, scalable system that is easy to deploy and extend, while Gridmo is a more complex system that is designed to support large-scale distributed environments with multiple data sources and processing nodes. Both systems include web-based interfaces and a range of visualizations and monitoring tools to help users optimize the performance of their computing environment. Grid portals are web-based user interfaces that provide a unified access point to grid computing resources, tools, and services. Grid portals are designed to simplify the process of accessing and using grid resources, and to provide a consistent user experience across different grid environments. Grid portals typically provide the following features. Resource discovery. Grid portals provide a way for users to discover available grid resources, such as computing clusters, storage systems, and data repositories. Users can search for resources based on criteria such as location, availability, and processing power. Job submission. Grid portals allow users to submit computational jobs to grid resources, such as batch processing jobs, data analysis tasks, or simulations. Users can specify the requirements for their job, such as the type of compute resources needed and the expected duration of the job. Job monitoring. Grid portals provide a way for users to monitor the progress of their submitted jobs. Users can view the status of their job, the current usage of grid resources, and any errors or warnings that may have occurred during the job execution. Data management. Grid portals provide a way for users to manage their data on grid storage systems. Users can upload, download, and manage their data files, and can also search for available data resources. Collaboration. Grid portals provide a way for users to collaborate with other users on grid projects. Users can share data and resources, and can also create and manage collaborative groups. Security. Grid portals provide secure access to grid resources, ensuring that only authorized users can access sensitive data or resources. Users must authenticate themselves with the portal using a secure login process, and may be required to use additional security mechanisms such as encryption or digital signatures. There are several open-source grid portal frameworks available, including Apache Errata, GridSphere, and Liferay. These frameworks provide a set of APIs and tools for developing custom grid portals, and can be customized to meet the specific needs of different grid environments. Overall, grid portals provide a powerful way for users to access and use grid computing resources, and can help to simplify the process of working with distributed computing environments. By providing a unified interface to grid resources, tools, and services, grid portals can help to increase the productivity and efficiency of grid users, and can help to promote collaboration and knowledge sharing within grid communities. Here are some examples of grid portals. The European Grid Infrastructure (EGI) portal. This is a web-based portal that provides access to grid resources and services across Europe. It provides a single point of access to a wide range of grid tools and services, including job submission, data management, and collaboration tools. Open Science Grid (OSG) User Support Center. This is a web portal that provides user support for the OSG distributed computing infrastructure in the United States. It provides a variety of tools and resources to help users access and use OSG resources, including job submission, data management, and collaboration tools. The Globus Toolkit. This is a set of open-source software tools for building grid portals and other grid applications. The Globus Toolkit includes a set of APIs and tools for developing custom grid portals, as well as a number of pre-built portal components that can be customized and integrated into existing grid environments. Apache Aravta, this is an open-source grid portal framework that provides a set of APIs and tools for building custom grid portals. Aravta includes a number of pre-built portal components, including job submission, data management, and collaboration tools, as well as a set of APIs for integrating with other grid services. Liferay, this is a general-purpose web portal framework that can be used to build a wide range of web applications, including grid portals. Liferay provides a set of APIs and tools for developing custom portals, as well as a set of pre-built portal components that can be customized and integrated into existing grid environments. These are just a few examples of the many grid portals and portal frameworks available today. The specific features and capabilities of these portals may vary depending on the specific grid environment they are designed for, but they all share the common goal of providing a unified interface to grid resources, tools, and services.